We've been talking about the Standard Model, trying to understand the conceptual framework and the players, the fundamental particles that make up the world that we live in. We've talked about all of the fundamental players that we know about today, except for one, which I've really only mentioned in passing, but it's a very important player, very esoteric, but also quite relevant if you want to understand how things work, and that's the Higgs boson, the Higgs particle. The Higgs is named after a physicist named Peter Higgs, and its role in the Standard Model, although it's quite formal and mathematical, it really is the thing that's responsible for the defining characteristic of any particle, its mass. So the Higgs plays this key role, and it also plays a role in distinguishing between those forces that are presumably unified now, weak and electromagnetic. And it also plays a role, potentially, in the evolution and development of the universe as a whole. It's quite unique in this respect that something very, very large scale, cosmology and the structure of the universe, may in fact depend and be determined by this subatomic particle. So today I want to talk about the Higgs. What is it? Why do we believe in it? It is definitely the most poorly understood part of the Standard Model to date. Everything else we've been talking about is extremely well established for many, many years now in the laboratory. The Higgs has been established mathematically, but not physically. We have no direct evidence of the existence of a Higgs particle yet, and it's big business in the physics world. There's a lot of money, a lot of energy, a lot of time and effort being devoted to finding the Higgs particle, and it has been in the news and will certainly be in the news again in the future. In fact, it has even played a role in U.S. politics, which I'll talk about today. So I think it makes it an interesting particle to learn about. Let me remind you, we've mentioned it before, but let me tell you about why the Higgs was proposed, what it does. We wanted to understand the weak force of nature, and it was believed, pretty much just because the other forces had gauge symmetry, that the weak force should also have gauge symmetry. This is a very abstract idea. It's a kind of a mathematical property of a theory that says if you shift something, physics doesn't really care. The world doesn't really care what number you choose to define as 0 volts in some electric circuit. So if you believe that gauge symmetry is a symmetry of nature, and we've already had extremely good evidence that it was a symmetry of electricity and magnetism and the strong force, so maybe the weak force too, if you want that, then you discover that the electric forces and the weak forces will be completely symmetrical in a lot of ways. They will not only be unified, the weak force carrier would be massless. Okay, and that's in direct contradiction with data. Every piece of data says that the weak force is very, very short range. It's like a contact. That's why it's so weak. A neutrino has to be right on top of another particle in order for you to have any kind of a chance of seeing a weak interaction in a certain sense. The force carriers, the W and Z particles, are massive. So how do you reconcile gauge symmetry, which says they should be massless, with the fact that they're massive? And the answer was a mathematical trick. It's the prediction or assumption of the existence of this new particle of nature. Now, when I talk about particle, right, in quantum mechanics you can talk about particle or wave. It's kind of two aspects of the same thing. And similarly, I can talk about particles or fields, now that we're thinking about physics as quantum field theory. The place where it's most obvious is when you're thinking about the force carriers. Okay, how do I visualize a photon, a particle of light? Well, first I visualize an electric field. I've got a little charge, and there's this invisible, maybe even abstract or mathematical electric field permeating space. That's not the photon. The photon is what you get if you wiggle that field. If you take the charge and make it move up and down, then the field will get a ripple in it, and the ripple will propagate through space. And it's that traveling wave, it's that ripple, that's the photon, that is the particle of light. And so every particle of nature can be thought of in the same abstract way as the ripple in a field. So Mr. Higgs proposes that there exists a new field of nature. It's not an electric field, it's not a magnetic field, it's what we now call the Higgs field. And if you have a ripple in that field, then you'd call it a Higgs particle. Now, the really unusual thing about this Higgs field, the thing that makes it special, it was the sort of brainstorm of these folks like Weinberg and Salam and Glashow and Higgs all putting the story together, was what if there's this particle, this field that permeates space. It's not zero, it's finite everywhere. Inside of atoms where there's all that empty space between the electrons and the quarks, outside, even in deep, dark outer space, there's a Higgs field everywhere, like a uniform background that we all live in. This is a wacky idea. I mean, normally we think about dark outer space as being pretty close to a vacuum. There's a few photons that travel through dark outer space because they're starlight, but pretty much what we imagine when we think of fields is you've got a charge and there's an electric field that's very strong near it, and then that field fades away. So as you get far away from things, you expect that fields should get very small. But not the Higgs. In order to make sense of the weak interaction, in order to make the theory mathematically consistent, we were obligated to postulate that there's this Higgs field everywhere. So as I walk through the room, I'm walking through like a sea of Higgs field. And what would the effect on me be? Well, it depends on the interaction of the particles in my body with the Higgs field. So that's also a part of your assumptions. Right now, all we're doing is playing a what-if game. That's how theory often begins. You just say, well, what if there was a field of nature that was everywhere? And what if most of the particles, the other fundamental particles, interacted with it? Okay? Well, one of the things that would happen is, as I'm walking, if the particles in my body are interacting with that Higgs field, there's going to be some sort of resistance to my motion. Now, what I'm trying to do here is to describe some very formal mathematics and make it concrete. And you have to appreciate, I'm always doing this in this course, and here I'm really stretching the metaphor about as far as I can. If what I was saying was literally correct, then you would imagine that all objects would come to a halt because they're walking through this goo. And that's not what happens. An object in motion remains in motion. Newton's laws are still true, even in the presence of the Higgs. But an object in motion feels more sluggish than it would if there was no Higgs field around. That's probably the best way to think about it. So we're kind of like fish underwater, swimming through this water, and it's always the fish who are the last to notice the water. And it's there, it's important for them, but they're going to notice other fish first, and they're going to notice the effects, maybe, of the water causing waves, causing things to move around. We live in this stuff. It interacts with our bodies. It's what creates the inertia, or in effect, the mass of all the particles. And yet, it took us a long time just to recognize the possibility of its existence. It's a very formal idea. And, when I was first introduced in graduate school to the Higgs mechanism, the mathematical framework, there's assumption after assumption being piled on. We're assuming a new field. We're assuming that it's not zero. We're assuming that the particles interact with it in specific ways. And then you start to now draw some conclusions, and those conclusions match all the weak data. In fact, lots more than just the weak data, the masses of the particles. Everything begins to tie in this lovely way that we've seen. The Standard Model is a beautiful, self-contained theory which describes the world. So on the one hand, everything fits together, and the Standard Model is a spectacular quantitative success. On the other hand, this Higgs business just seems pretty ad hoc. Now, maybe it's just because it's a more recent discovery. Way back in the early 1930s, Mr. Dirac proposed something very mathematical and formal, namely antimatter, and he could hardly believe it himself. And the same thing with the neutrino. Many of the particles that came out of mathematics were at first sort of viewed with suspicion. It seemed so formal and abstract. The quarks themselves didn't seem like real things. What we want is evidence, direct evidence, for the existence of the Higgs. Before I get to our search for the direct evidence, because we don't have it yet, okay, this is still a hunt, I want to say another word about sort of why the Higgs is such an important thing in this theory. In nature, the weak force and the electric force seem completely different. They are as different as night and day. One of them has to do with radioactivity, the other is everyday life. The carrier of electricity is massless, so it's really easy to generate electricity and electric forces but the carrier of the weak force is very massive, so it's highly improbable to have weak interactions occur. There is, in fact, a symmetry in the Standard Model that says that these two forces of nature are one and the same, viewed from a different perspective. So how does that symmetry get broken? How do you go from a universe where weak forces and electric forces are identical, that's some sort of mathematical or high-energy universe, to the one we live in, where the forces are so different? And the answer is the Higgs. It's the Higgs that's responsible for symmetry breaking. In the Standard Model, the W and Z bosons interact with this Higgs field that's everywhere. As they're traveling along, they, in fact, interact very strongly with it, and so it slows them down a lot. They become very massive. So it's the Higgs field that breaks the symmetry. We call this electroweak symmetry breaking. That's the fancy expression for it in the world of physics. And if you want to understand that phenomenon of nature, why does the weak force and the electric force seem both to be the same and to be so different? You got to understand the Higgs. There either has to be one or there has to be something else. If it's not the Higgs, if we're wrong in our guess, there's got to be something, at least we believe there should be some reason why the symmetry gets broken. I think we should be glad that the Higgs exists, if it does, because symmetry breaking is not a bad thing, it's a good thing. The world is much more boring when everything is completely symmetrical. Artists know this. When they draw paintings, it's very rare that they'll draw a perfect geometrical symmetry. It's the breaking of the symmetry that gets your interest. Imagine that we lived in a sphere, a very symmetrical universe, and it was filled with some gas, some water vapor. Okay? It would be a beautifully symmetrical universe. There's water vapor in all directions, the pressure's the same everywhere, and nothing interesting is going on. Life would get more interesting if you cooled down that sphere, and you cooled it down to a certain critical temperature where the water vapor begins to condense into liquid water. Okay, at that lower temperature, now you've got some physics going on. You've got a little pool of liquid water here and some vapor over there, and you can swim in the water and jump out of the water, and there's boundaries and there's physics phenomena going on. Life gets interesting. And that's sort of what's happened in our universe. We could imagine a universe, in fact, in an accelerator at ultra-high energies, higher energies than we've reached so far, or in the early universe, very close to the Big Bang, when the universe is, in effect, very hot, the electric force and the weak force become like this uniform water vapor. It's all the same. The two forces are identical and indistinguishable, and it's lovely and symmetric, but not so interesting, not so much fun to live there. In our universe, which has cooled off, the two forces separated, and so we get the two different distinct phenomena. So this is all kind of motivation for why we believe in it and why it might be important to our understanding of the world. So let me talk now about how you go hunting for a particle like this. It's, in a certain sense, like looking for neutrinos. Okay? You believe in them because there's a mathematical theory that predicts their existence. With the neutrinos, it's pretty clear from the theory how you should go looking for them, because the theory itself tells you exactly what the probability of interaction is. So you can figure out how to design a big detector. It's a little tougher with the Higgs, because unfortunately, the one thing that the Standard Model cannot tell us is how massive this Higgs field itself is. When I say how massive, I mean how much energy do we have to pour into a small region of space to create a ripple in that Higgs field? So I'm sort of imagining an unusual fluid, right? We're walking through this universe that's filled with not water, but Higgs. And what we want to do is create a wave. It's not like water, where just the slightest little perturbation will create a wave. That's a massless particle that's easy to make. The Higgs is massive. So you need to pour a lot of energy in to create a ripple, which would, once you've created it, it's a real particle, the Higgs particle. It would leave a track in a bubble chamber. It would decay into other particles. It would be as obvious as any of the fundamental particles if we could create one. There are a couple of ways you could imagine doing this. A direct search or an indirect search. The indirect search would be to look for the presence of a Higgs, because any particle of nature, if it's real, can be virtually created and then disappear again